And welcome back to the Turd Fur Viewing Network. Alright, today's video is on series and parallel circuits. Now, if you're looking for a basic video on this, you need to go to my physical science playlist and watch series and parallel circuits. This video is intended a little bit more for the physics audience that maybe already knows a little bit about this. But just in case you don't, a series circuit looks like this. You've got one resistor after the other, but by definition what makes a series circuit is the fact of this. If you have a current flowing through this wire, you're going to have that exact same current in every one of those resistors. So that's why usually for a series circuit we come back and say something like the amps, which is really your current, is the same when things are in a series with each other. So say for example, if there is 1 amp of current in this, every one of these resistors would have 1 amp of current flowing through them because there's only one place for this current to flow. Now series resistors are easy. If you want to add up, and most time in physics they call it the equivalent resistor. Most time in like 10th grade I just call it R tot, because it's your total or your equivalent. All you've got to do is add those resistors together. If you had 30 of them in a series, you'd add all 30 of them together in a series. And that's what you need to do for, and you might have other equations in the book. The reality is, this is all you need for series. Now, a parallel, by definition, a parallel, and usually in physics, this is what you'll see a lot of. But we could do a lot of examples of parallel resistors. All it means, that would be parallel. This one would be parallel. Let's see. You'll sometimes see this in physics books. Pictures that look like that. And again, every one of these represents parallel. And the reason why is because of the definition of a parallel circuit. All it means to be parallel is that when you have a current getting to this point, that current, we call these a junction in physics. When it gets to this junction, that current is going to split. So this current's going to go in 3 different directions. It's going to look for the path of least resistance. So wherever the smallest resistor is, that's where most of the current's going to flow. It's like water. It wants to flow through a less clogged pipe. This would be, same thing, there's a junction. This would be parallel because that current is going to split when it reaches that junction. And the same thing here, although people have a harder time seeing it. This spot would be a junction because the current could split and flow in 2 directions. And that's why when you study Kirchhoff's laws, you're going to actually be doing what's known as a junction rule, because a basic little rule, if we were sitting here doing Kirchhoff's laws, is whatever that current is here would be equal to the sum of those 2 currents. And that is one of the foundations of Kirchhoff's laws. Now, this is not a video on Kirchhoff's, however, although I will make one if you so desire. All you need for these kind of resistors, for parallel, it's just you add up like this: 1 over R1 plus 1 over R2 plus 1 over R3 plus, if you had 40 resistors all split in parallel, well, you just keep 1 over R plus 1 over R plus 1 over R and so forth. Now, the big thing to keep in mind though about parallel, in series we saw how the amps were the same on every single thing. When you're looking at something that's in parallel, and let's draw a parallel couple, let's just do, here's 2. There's 2 parallel resistors to each other. I don't care how big they are. I'm just drawing them in parallel. And let's put a potential or an EMF in the circuit over here. And we might say that it's like 10 volts. Well, if you have a 10 volt potential in this circuit, that battery, and you got to think about, what is the battery trying to do? The battery is trying to push electrons through this circuit, if you want to view current that way. It's trying to push charge through this circuit. And think about like somebody sitting on the bench press, where they got their 2 arms up in the air. And this is a terrible looking bench presser, but anyway, that's not the point. There's his nose. I don't know what I'm doing. But anyway, here's this guy bench pressing. And he's sitting here pushing. He's pushing both sides. He's exerting the same potential on both sides. And that's kind of what's happening with this potential in this battery. Each one of these resistors has 10 volts of potential being exerted on it, which means volts, better known as potential, is the same when things are in parallel to each other. So even if you had 2, 3, 4, if you had all these parallel resistors all connected together, and you had one 5-volt battery attached to it, if that were a possibility, what does that imply? It means there's a potential of 5 volts on every single one of those resistors in this problem. Now, believe it or not, in order to do resistor problems, you need this basic understanding, this little bit of knowledge. Amps, the current's the same in series. You need this equation, Megatron important, and you need this equation. The only other two equations you might ever need in any circuit problem, well, I'll go and tell you, the most important of all, V equals IR, Ohm's law. This is like, oh, look at the majesty. Oh, give it some majesty. Oh, it's beautiful majesty. You need this guy. He is, I'll be honest, once you do the R equations, this is the only equation you'll usually use again. Now, I know, you're taking a physics class potentially, which means you're probably also every now and then getting the word power snuck into a problem. Well, power is nothing but IV, or if you want to be, kind of pimp about it, I square R or V square over R, depending on the situation. But you may need to use your power equation at some point. And just remember, power is measured in watts. Or as I always like to say, watt is the unit for power. No, really, watt is. So anyway, let's move on and do a couple of examples here real quick. All right, so this is one of our problems out of WebAssign. And if we sit here and take a look at it, we've got 3 resistors, a 6, a 7, and a 10, and they're all connected to a 24-volt battery in this question. So let's start off. First thing it says is that they're connected in a series. So let's look at those sizes, a 6, a 7, and a 10 again. So let's draw us a picture. So we've got a 6, a 7, and a 10 ohm resistor all connected in series with a 24-volt potential. So there's my 6, there's my 7, and there is my 10. Now, what I would give you for first rule of advice on any of these problems is the same thing WebAssign asks. What is the equivalent resistance? Cool. Let's find this resistance. All you've got to do in a series is add your resistors together. Just sum up all your resistances in the series, and you've got it. And in this case, that would come out to 23 ohms. And if we go back here and check WebAssign, sure enough, bam, we've got that one right. So 23 ohms for our total resistance. Now, my next advice would be this. On every single resistor problem, once you find this REQ, go back to the battery and find how much current is leaving that battery. So there is my battery or my EMF, and so I'm going to come in. Now, I've already told you, the only equation I use from now on is V equals IR. And I know that the potential at the battery is 24, I, and I know that R is 23, and 24 divided by 23 would be 1.04 amps. And we can go back and check via WebAssign, sure enough, 1.04. But check this out. Let's go ahead and look at WebAssign. What are the currents in each resistor? They're all 3 the exact same current. Why would somebody do that? Well, we've already established. You just found that 1.04 amps of electricity leaves that battery. Follow it. It's like water in a pipe. Where's it going to go? It has no choice. That 1.04 amps has to go through here. and that 1.04 amps has to go through here, and it also has to go through here. Now, this problem doesn't ask you to do this, but I'll go and tell you, the only other question that you would ever be asked, this problem might ask you to do one of two things. It might ask you to find the potential, let's do this, the voltage, the potential. It might ask you to find that on this resistor. I have unopenable files. Or it might even ask you to find the power. And that's not too big of a deal. If it wanted me to find potential, all I'd have to do is I times R. It'd be about 6 volts. If it wanted me to find power, I could go I square R, which would basically be about 6 watts here, because I square would be 1 times 6. And so that would be the only other question we might be. And it could ask us this same question around every single resistor. It could ask us to find V, and it could ask us to find P on any one of these. And if, again, if it did want me to find power, my equations for power are IV, I square R, or V square over R, which in this case I would probably go with I square R. And all you'd have to do is 1.04 square times 10. And let's face it, that's basically going to be 10 watts. 10.1 watts, or 10.2 watts maybe. And that's all you'd have to do. But anyway, it didn't ask. That's the only other things it could be asked. Let's do C. C wants you to redo this problem again, but it wants you to make all of these in parallel. So let's take those same 3 resistors, and let's put them all in parallel to each other. And what I mean by that is, let's split the electricity. So we got the same 24 volts of potential, and then we've got a 6, a 7, and a 10 ohm resistor all in parallel to each other. Well, how about this? Step number 1, let's not even use a brain. Let's just go straight to do this. 1 over Req would equal 1 over 6 plus 1 over 7 plus 1 over 10. And I'm going to do this actually in a calculator, because I want you to watch how this goes. So, ooh, clear. 1 over 6 plus, don't you love a Casio FX 115? So incredibly awesome. Plus 1 over 10. That equals 43 over 105. Now this is where some of you mess up. That is not your answer. You see, the problem is this. You did not solve for REQ. You solved for 1 over REQ, which means if you want to find this equivalent resistance, this total resistance, you still need to take a reciprocal of this answer, which is easy in my calculator. I'll just hit this X negative 1 button, and my answer is 2.44, and all that other junk repeating up there. So my REQ is equal to 2.44 ohms. So you have to remember to take that reciprocal when you're doing this. And we can check our answer via WebAssign, and he says 2.44 up here, so I'm like, yay. Now, a very common thing, and I like to always do this, I always like to come back over to this battery now, and I like to know how much current is leaving this battery. Whether or not the problem even asks me, I'm going to do that, because all it is V equals IR. So 24 equals I times 2.44. Let's plug that in a calculator and see what we get. 24 divided by 2.44 equals 9.84 amps. So leaving this potential is 9.84 amps of electricity. But now let's look at something. What's going to happen to that 9.84 amps when it gets to this junction over here, as we'll call it? What's going to happen is part of the amps are going to go that way, part of the amps this way, and part of the amps are going through the bottom. So you're actually going to split this current into 3 separate amps is what you're going to end up doing. We're going to have 3 separate currents. Now you should be able to figure out where the bulk of the current's going to go. Most of the current is going to go through this 6 because he's got the least resistance. The least amount of current is going to go through the 10 because he's got the most resistance. So let's come back now and see if we can't figure this out. How can we find this I? Well, I've done told you, after you do this R stuff, the only equation we'll use from here on out is V equals IR. He's the only guy we need. So how can we find this I1, this current up here? Well, you got to remember something. I said at the beginning of the video, potential stays the same. My sexy science word for volts. Potential stays the same in parallel, which means there's 24 volts on that guy, 24 volts pushing electrons through this guy, and 24 volts pushing electrons through that guy. So if we want to find these amps, I've given you everything. There's your R, there's your V. So for the first one, 24 would be equal to I1 times 6. Hey, that's kind of beautiful math. 4 amps. So that means 4 amps of electricity are going through that resistor. And we can go through and do all of them. Let's see, the other one, 24 would be equal to I2 times 7. And that would be like 3.4, I guess, something in that ballpark. Here, let's find out exactly. 24 divided by 7, 3.43, not too bad. 3.43 amps. So there's my I2. And then for the very final one, how many amps are going through the 10? Well, you're going to love the math on that one. V equals I3R. Once again, notice something, 24. Every single problem's had the exact same potential because potential is the same in this parallel down here. 24 equals I3 10, which would be 2.4 amps. And now notice something. You found that there's 4 amps through the top, there's 3.4 amps through here, and then you just found out that there is also, what did we get? 2.4 amps through here. Well, look at something. It's a little way of checking yourself. Look at all these amps. What does it add up to? It adds back to 9.8 because that's how many amps or how much current left the battery. But anyway, this has got a very good introduction in terms of this. The only other thing you could be asked would be power. And if you were asked power, all you need is IV, I square R, or V square over R. You've got all 3 variables for each one of these, and you could find the power lost over any one of those. But anyway, we'll save that for another video. So Feliz Navidad.